So it seemed informally, when we graphed the slopes of y equals cosine x, we seem to get the graph of y equals negative sine x. Let's find out for sure by using the definition of the derivative. You can always use the definition of the derivative to find the derivative, and that's what we're going to do. So we're going to find the derivative of cosine x, right? So this means take the derivative of cosine x, and we're using the limit definition. So that's going to be the limit as h approaches 0 of cosine x plus h minus cosine x all divided by h. Now some things we can't do. We can't make that cosine x plus cosine h. That is not correct. Okay? You can't distribute the cosine. You take it's an operation. Right? You're taking the cosine of the sum. You can't break that apart. Right? But we do have some handy-dandy rules from pre-calculus, as well as some other limit rules we may use in this particular, not really proof, but finding the derivative, derivation here. And so that handy-dandy rule from pre-calculus we're going to use is if you have the cosine or of a sum or difference, right, it's going to be the cosine of the first times the cosine of the second, plus or minus. The sign is going to be whatever the opposite is. Right? So here I have a plus. I have cosine x plus h. When I rewrite it, it's going to be cosine x minus h. Right? And then sine of the first times sine of the second. Right? So now you're using those rules that you've learned in pre-calculus. We'll talk about the limit rules we're going to use a little later on, but right now we need to simplify that. Right? So we have the derivative. So I want to forget what, oops, too many x's in there. So the derivative of cosine x is the limit. And by the way, I almost forgot to mention, this goes in the notes that is in the packet, in the weekly work. Right? There's a space for it. Write these in there. Right? So we have the limit as h approaches 0. We have now cosine x. And then, so cosine x, cosine h. Cosine first, cosine second. And that's a plus, so this is going to be a minus. And then we have sine x, sine h. I'm looking at the next limit, right? Sine x, sine h minus cosine x. And by the way, I would recommend that you put all of this in your notes, right? So that in case, especially if you don't remember it, because you don't want to look back and go, how did we do that? Why did we do that? Oh, I don't understand that. Right? And then you'll remember, oh, what's that little ruler? All right, so things aren't looking really friendly here. We've got a cosine hanging out all by itself over here. Notice him. Let's move him over so he can be with his cosine friends. Right, so we have we're taking the derivative of cosine x, and that's going to be the limit as h approaches 0. And so anytime, by the way, you're finding the derivative, if you don't know another rule, you can always use this one. Always use the limit definition derivative. Right, so cosine x times cosine h. I just have things that are added and subtracted. I can change the ordering. Right, so as I just have, you can just think of that as adding a negative cosine x, right? I can have them switch places. Right? It's still plus a negative, sine x, sine h. Well, we're so used to, what happened to my line there, of combining fractions to simplify. In this case, we want to separate fractions. We want to create two fractions here, right? But I can't do that if the way I don't want to do it the way I have it now. I've got to do one other thing first. And that is I want to factor out a common factor. Because right here we have a common factor. So let's factor out that common factor so we can rewrite this one. So we're taking the derivative of cosine, and that's equal to the limit as h approaches 0. Let's factor out cosine x. Then we have cosine h minus 1, right? Because cosine x divided by cosine x is going to be 1, and there's a negative there. So we have cosine h minus 1, and then minus sine x sine h all divided by h. We could split this into two separate fractions, right? And each one gets an h, right? We have two terms here. That's why I wanted to combine them as a fraction. I mean, as a product. Now I have two terms. This is term number 1. This is term number 2. They're going to separate into two different fractions. The cosines, they want to hang out together, and they don't want to hang out with the sines. So we have taken the derivative of cosine x, that equals the limit as h approaches 0. All right, so now we've got cosine x times cosine h minus 1 all over h, because everyone's got to get an h here, right? Because I have a sum, I have a difference, right? Sum or difference, right? If I want to rewrite this as two fractions, everybody gets an h. It's going to be different for a product, but for sum or difference, everybody gets an h. And then minus sine x sine h all over h. All right, so now I'm going to rewrite my product just a little bit. So I'm taking the derivative of cosine x, so that's the limit as h approaches 0. All right, so I've got cosine x, and the only reason I'm rewriting this is just so you see it nice and clearly. All right, so I've got cosine x times cosine h minus 1 divided by h. If I want to split a product into two fractions, somebody takes the h, right? They don't both take the h, right? Because I still have cosine x times cosine h minus 1 divided by h, right? Because I've just rewritten my product so that instead of combining it and putting h over both of them, I just put h over one of them, but it's still the same thing, right? I'm just multiplying. Right? You can think of dividing by h as multiplying by 1 over h. Right? But I don't need to change that. I'm going to do the same thing here, right? I'm going to split my product, and the only reason I'm really doing that is so that you see this nice and clearly. Right, so I have sine h all over h. It wasn't actually a necessity. All right, so now we're going to talk about those limit rules that we're going to use. We're going to use the limit as x approaches 0. In this case, it's an h approaches 0 because that's what our limit is. But if you remember, we had two handy-dandy little rules from when we were learning trig limits. And one of those was cosine x minus 1 divided by h. That limit as x approaches 0, that was 0. It had no variety, no derivations, but it has that one. And then we have the limit as x approaches 0, sine x over x equals 1, and that one had lots of variations, but we don't need any variations. Right? Just take a look at this. Do you see a cosine h minus 1 or cosine x minus 1 divided by x? Right? Well, since our limit is not as x approaches 0, it's as h approaches 0, do you see one with h's? Hopefully you notice this one right here, right? This one right here is the exact same thing as the one we have up there. That's just 0, right? So the limit, as I can split this in and write the limit 4 times, but I think we all understand that each one of these is the limit. So as the limit as h approaches 0 of cosine h minus 1 over h, that's just 0. So now I've got cosine x times 0, and I think we know what that's going to be. But let's continue on. All right? We may as well keep working here. All right, so I've got a sine x. But sine h over h, what's that limit going to be as h approaches 0? Why, that's just 1, right? And that is straight out of right there and there, right? Just reviewing two limits. We're just using those two limits. All right, so now let's rewrite this. All right, well, cosine x times 0, well, that's just going to be 0. Anything times 0 is 0. All right, so now I've got the limit as h approaches 0 of 0 minus, and 1 times sine x, that's sine x. All right, I got no h's left, so we're done. And that means that the derivative of cosine x, that's equal to negative sine x. And that's exactly what we found sort of informally. And we found it because, well, quite honestly, I led you to it. But now we have solved it using our limit definition, right? And that is irrefutable, right? I could be wrong when I'm approximating it, but we're not wrong here, right? And so now you have another rule for you. You learned power rule. Now you got this one. All right, so the derivative of cosine x, that's negative sine x. All right, We're going to look at one more trig derivative in this one. And I think I'm going to keep going. I had to stop that other one as well. I needed to make the video into two. And a few things weren't where they were supposed to be, so I had to move them over. All right, so again, we're going to be graphing. Let's first, this is, before we graph the slopes, this is the slopes of y equals sine theta. Let's graph sine theta itself. All right, so we've got theta and sine theta, right? And just a little reminder, just put it way down here, right? So sine is y. All right, so right here, at that point there, at 0, 1, right? Excuse me, at 1, 0, sine, that's just going to be 0. Right? So so that point there, 1, 0, this corresponds to position on a coordinate plane. If we're thinking of our angle measure, right? We're here at 0. Now we're here at pi halves. Now we're here at pi. Now we're here at 3 pi halves. We can go the other way, right? If we go the other way, that happens to be negative pi halves. And if we keep on going this way, that'd be negative pi. The point itself is 1, 0, right? Because if we're talking about a coordinate plane. However, when we're graphing sine, we talk about the angle measure, right? So if I'm right there on the x-axis, right? There's no turn at all, right? So my angle, so that's what 0 is referring to. My angle is 0, right? And when the angle is 0, right, sine is the y value, sine is 0. Up here at pi halves refers to now the angle measure, right, of 90 degrees or pi halves. That point is now 0, 1, sine's the y value, so it's 1. Come around here to pi, right? So now I'm here at negative 1, 0. Right? So pi, that's the amount of turn, we're 180 degrees, or pi. Right? And sine, of course, is the y value. Right? So pi is 0. And then we're going to go in the other direction. Right? So 3 pi halves is the exact same thing as negative pi halves. Right? And so now here, the point would be, if I can fit it in there, would be 0, negative 1, negative pi halves. And I guess I should let me put them in order of, I just tend to think 0 first. But let's move them down so it matches the other. And then we'll stick the negative pi halves and negative, whoops, well, I guess we're not moving that one. We'll get rid of it. There we go. All right, so 0, 0. All right, and then for negative pi halves, and oops, goes the other way. Want to match. Negative pi and negative pi halves. There we go. All right, so negative pi halves, same as 3 pi halves, like I said. So that's going to be negative 1. And then negative pi, right, same as pi, that's going to be 0. All right, so let's graph those, right? And so let's write the values here. So this is pi halves, and this is pi. Of course, that's right there, 0. And then we have negative pi halves, and we have negative pi. All right, and so we'll graph ours. Of course, this is 1 and negative 1. So we have negative pi 0 and negative pi halves negative 1. Yeah, I think that's about right. And then 0, 0. And then pi halves 1 and pi 0. And of course, it just keeps doing the same thing over and over and over again because, well, it's cyclic. Right? It just keeps doing the same thing. There we go. All right, so the reason we graph, of course, the sine graph is I mean, yeah, I have a table of values there telling you what the slopes are, but it's a lot easier to visualize it. It's a lot easier to understand when you can visualize it. All right, so now this graph, the black graph, is y equals sine x. And the red graph is going to be y equals the slopes of sine x, just like we did before. All right, so negative pi, you can see we appear to have a slope of -1 there. Right? And that's what's in our table there. Negative pi halves, I think you can see we have relative max. That would be a slope of 0. Right? This would be the opposite, the reciprocal of what we had for negative pi. Now we have a slope of 1. Pi halves, I think you can see we have another extreme value. This time it's a relative maximum. And then I think I'm a little too rounded there, but our slope coming down the hill at pi there is also -1, and then it just keeps on, it's going to continue on and do the same thing again. All right, so let's graph these. All right, so negative pi is -1. Actually, let me write in 1 and -1, and let's, maybe it'll be in red. We'll just make everything red here. So negative pi halves, 1, -1. This one's 0. This one's pi halves, and that's pi. Oops. Well, my mouth said pi, but my hand decided to want to write pi halves again. Probably because my allergies and my eyes are all itchy. And so I keep blinking, so I can't watch what my hand is doing. Negative pi is -1. And negative pi halves is 0. And 0 is 1. And pi halves is 0. And -1. All right, and so now let's graph. And oops. And I missed my point. Still missed the point. All right, there. The point moved. It's out of my line. There we go. Yeah, but it's not going down, it's coming back up again. It's really not that hard. Sometimes on the smartboard. There we go. Well, it looks like somebody kicked it in a little bit on the left side there, but I think it's okay. And as we look at this, that graph, if we went back here, where I think the graph looked a little nicer, it looks a lot nicer. Doesn't it look an awful lot like y equals cosine x? Except somebody sat on it. So it looks like, let me make that nicer. I'm embarrassed for the graph. It looks like that when we graph the slopes of y equals sine x, it seems that we get y equals cosine x. So it seems like the slopes of sine x give us y equals cosine x. And of course we know that the slopes of our function give us the derivative. Right? Usually we can't find a derivative just by graphing a bunch of slopes, right? But it can give us a hint. Right? Let's see how good our hint is. And of course, let's go back to our definition of the derivative, right? Limit definition of the derivative to find the derivative of sine x and see, is it really y equals cosine x? And you have a spot in your notes for this one, and I want you to do this one too. And it's in that weekly work packet. All right, so we also have a handy-dandy little rule to help us out with sine, because we're going to have, we already have it written up there, we have sine x plus h, right? And you can't distribute the sine to x and h, that's nonsense, right? You have x plus h, then you take the sine of that. But we can't add x plus h because they're not like terms, right? But we have a way to deal with that, just like we did with cosine, right? So it's going to be sine of the first times cosine of the second, plus or minus, this time the sign is going to match, and then cosine of the first times sine of the second. All right? Handy dandy little rule from pre-calculus. If you don't remember that rule, you should write that rule down because it's right over there, right? So write that rule down. All right, so we're going to we're differentiating sine x using our limit definition. All right, so we have the limit as h approaches 0. So we're going to have sine of the first, sine x, times cosine of the second. Right, so it would be cosine h. We got a plus there. It's this plus, not that minus sine x. That's not, we're not using the rule for that. That's just minus sine x. All right, so that's a plus. So that's going to be a plus. And then we have the cosine of the first. So cosine x times the sine of the second. Sine h. All right, so everybody's there. And then we have minus sine x. Right? And we're going to divide all of that by h. All right, so let's see what we're going to do about this. On the last one where we were looking at cosine, we were finding the derivative of cosine using the limit definition. We put all the sines together and all the cosines together, right? Can't really do that here because we got sines and cosines all mixed up. But perhaps we could at least put the sine x's together, right? So we're going to change the order that we're adding the terms in because that doesn't make any difference. Addition is commutative, and technically minus sine x is the same as plus negative sine x. Right? So I have sine x cosine h, then minus sine x. Let's put him over here. And then let's put the plus cosine x sine h. Right? Again, I see I have, although divided by h. And we have some like terms, right? Not like terms, but a greatest common factor between those two terms. Let's factor that greatest common factor out. Right? So we're taking the derivative of sine x, and that's the limit as h approaches 0, and we're factoring out the sine x. That's going to leave us a cosine h minus 1 plus cosine x sine h. Wonder if you know which way I'm headed. All over h. Hey, let's rewrite these as two separate fractions. Did you know I was going to say that? All right, so let's take the derivative of sine x, which is just the limit as h approaches 0, and then let's write sine x cosine h minus 1, oops, lost a parenthesis, minus 1, all over h, right? That is we have a sum or difference there. In this case, it's a sum. So everybody's got to get an h. Right? And then cosine x sine h all over h. This is a little uphilly here. All right, so let's split that. And the main reason I'm splitting that is so that you can see it nice and clear with no issues at all. All right, and so I'm just going to split my product there. All right, so we're taking the derivative, oops, and we got an x where it doesn't belong, because that doesn't mean take the derivative. So take the derivative of sine x, which is the limit as h approaches 0. I think we can make a song out of this. So we have sine x times cosine h minus 1 divided by h, right? Because it's really just sine x times cosine h minus 1 times 1 over h, and you're multiplying three things together, and the order I multiply in doesn't matter. Right? And so now let's do the same thing over here. All right, so we got a cosine x times a sine h divided by h. All right, same thing. We got cosine x times sine h times 1 over h, and it doesn't matter the order we multiply in. All right, so now taking the derivative of sine x, and that's going to give us a limit as h approaches 0, and my h looks more and more like an n as we go through this thing. H approaches 0. All right, so you have sine x, and then cosine h minus 1 divided by h. Same format as this one, right? Just a different letter. The variable doesn't matter. All right? So when we have it, remember that from we were learning trig limits, right? That particular limit has no varieties, but that one is 0, and that's what we got. So we got sine x times 0 plus cosine x. Anytime you see sine of something over the same something, when you're taking a limit as that something goes to 0, you should be thinking that that limit is 1. All right, so anything times 0, that's going to be 0. I think I must have wrote larger in this one because I'm running out of space. I also wrote it downhill a little bit. I'm just going to move everybody up because I need like one more line. And I don't like to write it at the bottom of the page because then nobody can read it. All right, so we have, for the last time I'm writing derivative of sine x equals, we got the limit as h approaches 0. This is just going to be 0, right? Sine x times 0 is 0, plus a cosine x. I got no place to put an h, just to substitute an h in because there's no h's left. But it does mean that the derivative of sine x is cosine x. And that looks just like what we saw when we graphed the slopes. And well, quite honestly, that's because I led you right to that a second time. All right, but now we know, no doubt about it, right? We've used our limit definition, and that will give us a limit. There's no estimation, no approximation. It's exact. We know our limit, our derivative of sine x is cosine x, right? And that's our next thing. All right, so you should have those, I don't know if it's 2 pages or 1 page on, I think it's 1 page, and you have half a page for each one. And at the bottom it has the derivative of cosine x and derivative of sine x, and hopefully you filled those in, because now you've got your third derivative besides the power. Well, actually you had the power rule, and you had the constant rule, multiple rule, and you had some indifference, but now you've got the derivative of sine x and cosine x. So let's do a little work, now that we did all that work, to determine without a doubt what the derivative of sine x and derivative of cosine x is. Let's solve a few problems with those. Right? And actually the bulk of this lesson was actually just finding the derivatives. All right, so constant multiple rule. And by the way, I've had to keep these problems simple because all you've got right now in your toolbox is power rule, constant multiple rule, and sum and difference rule. And now the derivative of sine x and derivative of cosine x, so I couldn't do anything more than that. So this is certainly not the end-all be-all in terms of difficulty on these problems, just so you know. We'll be doing more things with them. But using just the rules you have, just the tools you have, let's find some derivatives. All right, so we want to find the derivative with respect to x. Y equals 2 sine x. I like to be precise, all right? And if there's a y, I write dy dx, all right? That format for the derivative. I quite honestly never use y prime. It's kind of the sloppy way. And you'll see it, and it's fine. But in my own writing, I write dy dx. First of all, you can easily lose a prime symbol, and it's a lot easier to notice dy dx. However, if we're not in the if we're in the function notation, I do keep the function notation and write f prime of x. To me, the prime doesn't really get lost as much because, well, it's sandwiched in there between the f and the x, and it keeps the same format. All right, so now that we've written and actually dy dx is the derivative of y with respect to x, right? So we have to take the derivative of everything we see. We took the derivative of y, that's dy dx, right? Make sure these are equations and you have dy dx and f prime of x, depending on whether it's a y or an f of x, or a g of x or an h of x. All right, so when you have a constant multiple, it's still that derivative times that value, right? Because even if we had a limit, right, and we had a constant multiple, we could factor that constant multiple out and it would just be 2 times the limit. So we know the derivative of sine x, actually I'll write it over here just as a little reminder. The derivative of sine x is cosine x, right? So the derivative of 2 sine x is 2 cosine x, right? Not too difficult there. And also another little reminder, the derivative of cosine x is negative sine x, and we saw that with the limit definition. So we want to find the derivative of negative 3 cosine x. That's just going to be negative 3 times negative sine x. And I do like to write it like that because then you don't accidentally make a mistake thinking, oh yeah, the derivative of cosine x is negative, but now you got two negatives, so it's a positive. 3 sine x. So f prime of x is 3 sine x. And there we go. Those two are done. Let's do a couple more before we run out of problems and run out of time. All right, so we have sum and difference rules, right? So the sum and difference rules state that if you're taking the derivative of a sum or difference, it's just the sum or difference of the derivatives. That's what that says up there, this right here, which you have in your notes with power rule. All right, so I just take the derivative of each one of them. The limit's the exact same way. All right, so I see a y, so I'm going to write dy dx. All right, derivative of sine x, that's cosine x. Derivative of cosine x, that's negative sine x. And that one's done. Derivative of y is dy dx. I've got 2 cosine x. That's going to be negative 2 sine x, right? Because actually, I'll just to make sure, there's no confusion, 2 times, right, negative sine x. Because the derivative, we'll write it again. The derivative of sine x is cosine x, and the derivative of cosine x is negative sine x. All right, so we have 2 times negative sine x minus 4, and then derivative of sine x is cosine x. And so we can simplify that. So dy dx, by the way, I forgot to mention. So these problems here and the other problems, those are in the one-pager of notes, right? That one little page of notes. All right, so let's finish. All right, so dy dx is equal to negative sine x minus 4 times cosine x, and we're done with another problem. All there is to it. Till we get some more rules. All right, so slope of a point. We want to find the slope of the tangent line to the graph of f of x equals 3 sine x at the point where x equals pi fourths. All right, so just as a little reminder, you should put this in your notes so you never forget to find the slope of the tangent line. You're just going to find the derivative and evaluate at the given x. In this case, the x we're given is pi fourths. Which is a nice value for them to give us. All right, so we have f of x equals 3 sine x. Take the derivative, f prime of x is going to be, derivative of sine x is just cosine x, so it's 3 cosine x. All right, so now if we want to find the slope, we just evaluate f prime of x at pi fourths. And that gives us 3 cosine pi fourths. All right, so a little reminder. Pi fourths splits this in half, splits that first quadrant in half. There we go. That's pi fourths right there. Right, and of course, that's an angle measure. Right, so pi fourths, half of 90, right? It's 45 degrees. This is your isosceles right triangle, 1 square root of 2. Right? Cosine is not really much matter here because sine and cosine are exactly the same, but cosine uses adjacent over hypotenuse. All right, so that's going to be f prime of pi fourths equals 3 times, so I'll just put it over here, cosine, actually I'll put it in green. I'll match my coordinate plane. So, and you should probably put this in your notes too. Cosine pi fourths is equal to 1 over the square root of 2, or we usually like to rationalize that, square root of 2 over 2. All right, so we've got 3 times the square root of 2 over 2, right? And we should simplify that so we don't have quite so many numbers there. So f prime of pi fourths is 3 square roots of 2 over 2. And there we go. That's our answer, and that's everything. All right, so hopefully these are all making sense. We got just a couple more problems left before this video ends. I don't know how many I got left. I got 1, I got 2, and then I got a few more, 3, 4. So you know what? Since, normal curve. Since I got a few more than I remembered, let's take this opportunity to end this podcast, and I'll start with the next podcast. So we're just doing some more problems, solving with the derivative of sine and cosine. All right, bye for now.